Hello again. This is Nick Vasiloglu with your research ML at Relational AI. A few months ago, we talked about the trends in machine learning at the ICLR 2022, but this last July, we also had ICML taking place in a hybrid mode. This time, we got to see each other. And we are going to talk about what we saw and what made an impression, and try to summarize it for you. Again, full disclosure, this presentation reflects personal opinions. There might be papers that we missed. Every time we go to a conference, we find a paper that has a reference from another conference that we completely missed, but we just have to keep searching. This time, we did spend we ended up spending a lot of hours to go through that conference again. We thought it was a bit less, but we had the help of Zeta Alpha. Go look at them. It's a really good website where you can kind of like visually navigate through the papers. Okay, so things haven't changed a lot since ICLR. These two conferences had only 3 months, 2 or 3 months lag. But ICML also verifies what we saw at ICLR. So language models are everywhere. They keep expanding and they keep coming closer to production. So they, as you expect, they're going to dominate this presentation as well. But we also saw other things. So there are some other smaller things that they might escape the attention, but Vocal Wabbit is probably one of the first industrial scale machine learning software that dates in the pre-deep learning era. It's kind of back. You know, bandits never die. We pointed to talks and that went into recent advances of Vocal Wabbit. So I highly recommend watching them, and also trying Vocal Wabbit is a really powerful tool, much lighter than deep learning, and always quite effective. You know, another thing that we also noticed, and it's reflected in the publication, that there seems to be a growing need for verification and certification for models. In my opinion, this is a new line of business. At some point, it's going to become something like ISO or SOC 2 for ML. Now, it's not the first time that we see non-autoregressive transformers, but we saw more papers, and as probably you're going to realize, there's a big race about scaling deep learning and reducing the cost and the energy. There's multiple paths. We're going to see, you know, some of these directions in this presentation. Maybe I should create another presentation now that we have all these conferences and talk about it, because this is really the race right now. Who's going to get cheaper and scalable deep learning models? Obviously, language model is one of them. So one direction is the autoregressive transformer. The other thing is you know, if you are in machine learning, you've heard the term generalization. This is something that we learned from the first class, overfitting and generalization. But I feel like generalization has been generalized lately. So in the beginning, it was something that's outside of the training set, but now there's other forms of generalization. First of all, when it's out of the distribution, but which means that you're seeing the same concept. Let's say you're seeing cats, but you're seeing cats that they are in North Pole or in places where you haven't seen them before, but you're still looking for them. But in some cases, the out of distribution means out of concept. So you trained your model for cats and dogs, but now it starts, you know, performing well on tasks that you know, involve lions or other animals or other you know, subjects that you haven't really trained your model. And basically, there were a lot of papers, some of them quite interesting, trying to understand the error landscape and what it means out of concept and what it means out of distribution. No, the papers never stop surprising us with new ideas that they challenge the fundamentals of AI, machine learning. So there's a growing effort to move away from backpropagation and rethink gradients and training process. I think it's pretty much everywhere you go, it's gradient descent, and we would have expected by now that this is considered something untouchable, but apparently, there's evidence that there might be better ways for training neural networks. Again, another direction of cheaper, faster, better. Now, in that spirit, sparsification, making neural networks that are sparse is another direction. And there's this technique called lottery tickets. We're going to talk about that later. We talked about it in previous talks. Is still the state of the art and is becoming better and better, but it's not the only way. Now, another thing that I wanted to mention is this method called mix-up, which is probably 2 or 3 years old, maybe less. And it has become the most popular method for self-supervision. Again, self-supervision goes hand in hand with language models. We're going to see a lot of papers about self-supervision. But mix-up seems to be a simple trick that has a very big effect. And, kind of like a last comment is that language models are taking over reinforcement learning slowly. So we see them becoming popular over there and replacing some of the traditional techniques. Now, the first day of the conference, you have the expo, and the next day is the tutorials. So we watched some of these tutorials. We're not going to mention them here. They are self-explanatory, and that's kind of like the idea behind them, to watch them by yourself. So the first one was challenges of applying graph neural networks that we liked. A question we're trying to ask over there is, are GNNs better than transformers? And I won't tell you what I think, but I think it's worth watching it and forming your own opinion. Again, I think undeniably the climate change is a hot topic wherever you go, and there is some guilt from the ML community, because we contribute a lot to the carbon dioxide emissions. So climate change and machine learning opportunities, challenges, and considerations, especially if you're studying your research life right now, you're looking at a topic, there's a lot of interesting problems from over there. Obviously, reducing energy waste, run the world more efficiently, causality and intervention, what's kind of like the best thing to do and when. And again, we talked about our guilt for the CO2 emissions. And the last tutorial is something that everybody's, there's kind of like tribal knowledge here and there, and there are no books or extensive tutorials about how to train and serve big language models. Okay, so welcome to the big model era, techniques and systems to train and serve bigger models. With the current scaling trends of CPU, GPU memory, you need decades to train a big language model on a chip. This is one of the problems right now. So if you want to do it now, you have to do it in multiple chips. So if you don't, you basically need to distribute and parallelize everything. So that's a great tutorial that explains the trends. So very quickly, I would like to keep this presentation smaller than the previous one. So I'm going to mention a list of papers but I'm not going to go through all of them. So 13 papers we liked at self-supervision. We're going to see some of them. Okay, so we talked about that in the ICLR 2022 presentation, but CNN is not anymore the undisputable champion in vision problems. Okay, for many years we thought that this is the best solution, but the vision multi-layer perceptrons, that's what the MLP stands for, where you do a simple idea of permutation. It's worth looking at the original paper, it's in the references, performs really well. And basically, if you make them a little bit more complex, not more complicated as a transformer, they become very, they're still less complicated as a transformer. Okay, they beat the vision transformers, they beat CNNs, and they're much simpler in architecture. So a paper worth looking at it. And then some simple techniques for data augmentation. It's very similar to mix-up. So the idea is that if you have a set of augmentations to apply to an image, cut the image in two and apply two different augmentations. So you see, for example, here, they apply two different filters on this bird. Okay, so cut it in different directions and use, maybe you cut it in 3 or 4 ways and do different augmentations. Apparently it works much better. Okay, that was kind of like a funny idea. You know, I don't know if you remember in the All Kids magazine when you're reading text, and you know, instead of having a word, it was replaced by an image. Okay, this is apparently a great way for training language models. So mixing text and images. Obviously, you don't put, you know, you put the embeddings of those, okay, in a row. Apparently, it works really well. I mean, if you think about it, every time you had to read a text like that, you had to put a lot of brain power to go between one representation and the other. In a sense, you know, if some of it was written in a language that you didn't know, it was also helping you learning new language. So, you know, a simple idea with a big impact. Okay, so this is called Data to Vec. So it's a general framework for self-supervision. So, I mean, we all know this idea of the masking, and you're trying to predict what the mask has, and you apply that to images, you apply that to speech, you apply that to text. And basically, the main idea is try to predict the next embeddings from the previous ones, but the idea is that you're also mixing a student, you're putting a student in the process. That's why it's called data distillation. But anyway, if you kind of want to get an idea of a unified framework for pre-training, this is a great paper. Then label towards perfecting mix-up. Again, I talked about mix-up. You'll find a previous presentation, more papers about that. The idea over here is that in some cases, mix-up can make errors. So people went through that, you know, in a more theoretical, rigorous way, and they tweaked it a little bit to make it even better. Okay. I know I'm going a little bit fast, but there's 2 concepts in unsupervised or self-supervised machine learning, if you want. The one is called label smoothing, and the other is called knowledge distillation. And they're kind of like there's kind of a debate, you know, how they are related and how they should be combined. So they're both based. They have a small difference, but they're both based on the fact that if you have an image that you say, okay, here's a dog, 100%. Now, if you pass it through any deep learning model, it will still tell you it's a dog, but it will say, it's 90% a dog and 5% cat and, I don't know, 5% a wolf. Now, these smooth labels, this is a way of getting like a label smoothing, apparently are very, very important for training subsequent models. Now, in knowledge distillation, you use these smooth labels to train a student. Now, here's kind of like a summary, if you want to go quickly, the difference between label smoothing and knowledge distillation and how you can combine both of them. We talked about mix-up before, found mix-ups again over here. So the idea of mix-up is basically that you take 2 points, okay, with their labels, and you're taking a linear combination of these 2 points, a third point over here, and you're getting a linear combination of the labels. So if you have a cat and a dog, you mix them up to something that it's in between, and you say it's 60% cat, 40% dog. And so this new data point with this new label, if you use it, it's really great. Helps improve your performance, your training. Now, the question is, how do you do this for graphs? Okay, and apparently it's kind of like the same way. So this paper tells you how to do it. You're basically creating new nodes, and you combine the edges. Okay, so contrastive learning is, in my opinion, part of self-supervision. So the contrastive learning is, for those who don't remember, if I have, I'm just picking 2 points. If they're coming from the same class, I'm saying that, sorry, I'm taking a point and I apply to different transformations. And because they have to be the same, they say that these 2 representations should be the same. Now, if I take a point and another random point and I do any augmentation, this should be far apart. Now, interestingly, we have these data augmentations for images, for text, for sound. But when it comes to combinatorial problems, so when you want to train a system that is going to provide a solution to a SAT solving problem, we didn't have a technique like that. But basically, here's an example. If you are in that field of SAT solver, there are some rules by doing elimination, okay, and rewrites. So basically, what happened is that we take these rules and we teach the system how to do these rewrites. Okay, so we're saying that from here you can go to here, or you can go. These are equivalent forms. So this is kind of like your pre-training. So using that, you can train systems that they can solve efficiently combinatorial problems, and you see some impressive results over here. Okay, I won't go. This is a little bit more complicated over here. It wasn't very clear. Just like the improvement. So SimClear is kind of like the state of the art for contrastive learning. Here, what you're doing is you're having, you don't treat. So here's the problem: when you pick a point and you do the data augmentation, you have some long tail effects. So points that they are on the long tail, you have to treat them differently. And the way that they're doing here is with boosted memorization. So you're looking a little bit at the history to help you do things. Okay, I forgot to mention that in some categories, you're going to see this box over here that talks about workshops. So we're going to talk about the workshops in the end. I should have put them in the beginning, but I just kind of left it for cooling down. So for language models, we have 28 papers, or probably more. Those were the ones that I chose. And there were 2 workshops. The first workshop on pre-training perspectives, pitfalls and paths forward. And then something else called updatable machine learning, because you often need to update language models. Now, in my opinion, when I say this, if you, let's say, had one day to spend on the conference, and you had to either devote it into going and watching presentations from the main conference onto workshops, I would prefer going to the workshops. They are usually more specialized, more focused, and you see amazing things over there. So if you really have a lot of interest in language models, and you want to kind of like see the big and the focus picture at the same time, I suggest you spend your time in the workshops and not on the papers. Okay, so now if you chose to look at the papers, let's focus here. So black box tuning for a language model as a service. So everybody knows that you can go to OpenAI and other organizations and create an account and use, the GPT-3. There's others as a service. You can't really, it's very hard to install it on your own cluster. So, but if you want to, let's say, optimize it or customize it to your own task, although it's pretty fantastic, but in some cases you need to do that. Like you need to fix your prompting and everything. You don't really have access to the gradients. So what the system is doing over here, it's putting a really, really small network on top of your language model service, and then it uses black box optimization, derivative-free optimization to train it, so that you can optimize your performance. Very practical if you intend to build things on top of language models as a service. So again, this is kind of like in the same spirit, where you basically extract labels from. So in some cases, even if so this in the previous case, I told you I saw your way of using constantly and sending requests to your GPT-3 language model, whatever you have over there. Now there's another way that you can still use GPT-3 to generate labels and BERT and multiple models actually, so that you can train a smaller MLP for your task. A great idea. So if you don't really want to keep paying dollars every time you have a request, every time you spend some time extracting the labels from GPT-3, asking questions, and then you use them to train your own MLP. Very, very useful in cases where you're not going to have internet connection. Also very good paper over here. So we have, a lot of, so you have the language, you have basically three types of language models, like the causal decoder, the non-causal decoder, causal decoder, that would be the GPT, that would be over here the non, that would be the BERT, and the encoder decoder is the D5 architecture. Now the question is, which one should I use? So they have three findings over here about which one you should use and how. It's a really nice practical paper about which architecture to use and how to train it. Now, this is also, I mean, you realize the common thing, everything is about saving money. In machine learning over here, this is more about choosing the right pipeline. So basically, you're running different slides. It's more like an AutoML, actually, is in the title, process of finding out the right pipeline for solving your problem. Okay, now this is a case of a paper. When we read it, we'll say, what is this thing about routed language models? And then we realize that we missed in previous conferences this idea of a routed language model. So this is obviously a paper by Google Research and DeepMind. Interesting, but in order to understand it, you really need to know what a routed language model is, and you can find it in ICLR. I think that was 2021, and switch transformers. All of these 4 papers over here are are based on routed language models. So the main concept is that the routed language models have superior performance. They require less flops. Now, you see over here, this is the number of flops. So they do give better perplexity. The lower is better. Okay. Now, they're about, let's say, like 50% or 80%, or so in that range, better or faster than the other ones, but they're not like orders of magnitude better. Okay, so it's a reduction. The idea is quite simple. I mean, if you're familiar with the traditional transformer, after the multi-head attention, you have a feed-forward layer. So this is a very dense computation. Okay, so usually it's a big, nasty matrix multiplication. You have that several times. Now, what they do is they replace this with a gating. So there's a gating layer that either does this or does that, or that, so it decides which, a smaller, it selects a smaller feed-forward layer. That's why. So that's typically 3 to 4 times smaller than this one. It goes like the gains are quadratic over here, but you still have the attention head. That's why I'm saying you get about something in the order of like, let's say in the same order of magnitude, but much less improvement. Now, in some cases, they don't switch completely to mixer of experts, as they call it, but they mix them with fully connected layers, and here they have some results. So you see here the cost and the accuracy, so 50%, 60%. Okay, and actually you do have some gains in the performance. Okay, so this is an interesting paper. It's not very easy to understand, but basically this is a transformer that learns how to generate a CNN. So that CNN then is used to do image processing. So that's kind of like, I found that interesting, that you have a neural network that generates another neural network on the fly. Now, let's see this paper over here. This is more on the self-supervision side, but yes and no. So it's the pre-training. I put it here, the transformers. So the idea is, in the transformers, usually you're trying to predict the next pixel or the mask pixel, but here you're trying to predict the position. So you're given, this thing unscrambled. So you give these patches, but we don't really tell you which is, where they belong. So it's scrambled, and you have to unscramble them. And according to the paper, they do have some results over here. They do have better performance in when they pre-train it that way. Okay, now I did have a longer session talking and explaining the non-parametric language model in my ICLR 2021 and ICLR 2022. This is a very promising, direction of scaling language models. So the main idea is that you train a small one, let's say a few million parameters, hundreds of millions of parameters. And then what happens is that, you pass everything through BERT. So you create a big, you take billions or trillions of tokens or sentences or corpus, and you pass it through a BERT or whatever you have, which has been trained on a smaller model, and you create kind of like a corpus. And when you want to make a prediction, then you basically sorry, you basically do you cast it as the nearest neighbor problem. This has been proven to be quite stable. It has a lot of advantages in the sense that if there's a mistake, it's much easier to correct it. You go to your database and fix it or remove it or update it. And it takes much less to, so basically you're less to train because your model is smaller. Another direction of winning the race of cost. You're basically trading computation here for memory, because you might really need, you know, petabyte, I don't know, terabytes of even petabytes of storage to do your nearest neighbor. And this technique like improves that. You know, it's making an improvement. It's making the inference a little bit more complicated, not that much, but you know, the results are amazing in terms of performance and in terms of computation savings. So far, it looks one of the most promising directions. Again, Unirex is a language model that is also trying to, you can think about it as an importance predictor. So when it, you know, when it's trying to predict something, so this is your task, you know, whether it's positive or negative, and this is also trying to highlight why it made that prediction. So a good direction in terms of towards explainability. This paper talks about Platon, about how you do, how do you sparsify your language models, and it's kind of like one of the basic techniques when you're doing a sparsification is, you know, you start training your model, you see if something has like a low weight, and you just like prune it. So you start pruning your network. Some algorithms do it in the end, sometimes sometimes midway, sometimes in the beginning. Now, this paper, what it really does over here says, okay, this weight seems to be a low amplitude, but if it's high variance, maybe I should give it another chance and I shouldn't really prune it immediately. So it pays more attention to low importance but high variance features in order to improve the results. And here you see the goal of the prune networks is basically not to move far away from the performance of the dense network, because that's kind of like the price you pay. Okay, one of the biggest privacy problems of language models is the fact that as you are training data, they tend to memorize things that they're not supposed to, like social security numbers or things that they are on the web and they shouldn't have been on the web, or the person has the right to forget. You know, one of the biggest problems I think in Europe, even in the United States, if there's something that you wanted to be removed about you, you have the right, at least I know that, the right to forget. Unfortunately, that right has been preserved on language, public language models that have been trained on the web, and people don't want this fact to be there. Maybe because it was wrong, maybe it was for any reason, it was untrue. They want to remove it, and they can't do it. So this curve here is very interesting. It basically tells you that the reason of memorization is the duplicates. Okay, so the more duplicates you have, this is the curve that shows you perfect memorization, and you see for different models, as you're having, the more duplicates you're having, the closer you're getting to this memorization curve. So the solution is simple. Before you train your model, remove the duplicates, and that is gonna save you a lot of problems when it comes to memorizing things that you shouldn't memorize. Now, I don't want to go into the details. That's also not my field, but I was kind of like interested in the fact that you know, auctions, they basically fuel the web with the advertisements. Now they also seem, the transformers seem to play a role over here. It's not exactly a language model, it's a transformer. Don't we shouldn't get confused over here. So I just found it interesting as a fact. Okay, so what if you were a transformer farmer? So I've called someone who grows transformers, who trains language models. Needs to be very careful. So this, I just picked this figure from the text. So the main idea is that, if you want to train a GPT-2 large, I don't know how many parameters, is a few billions, as far as I don't remember the exact number. Okay, no, it's 768 million parameters. You can create that model and start training with a full data set. But apparently, you can do better. So you can strive with something which is 1/4. Again, another ways of reducing the cost. And you go up to this point, and then you slowly start increasing. And actually, then you quadruple the size at this point, and you insert more training points. So basically, you get to that performance. So in some cases, you can get better performance. But the main idea is that you get a faster convergence. Okay, so growing transformer into stages is the best way to go. Now, again, we see that problem we talked about before, which called there was even like a whole workshop about updatable models. Editing a large language model is not easy. So if you ask today, it just happens the day that the Prime Minister in UK changed. What's the Prime Minister of the UK? All language models are going to be wrong because they were trained with whatever with past information, and editing them. This is an incremental move forward, but it's still very complicated versus the symbolic ways where you just like go to the fact and you replace it. But finding where the problem is and changing it, it's not easy. So let's see. We still need progress over there. Okay, so this paper, again, see how the two competing architectures, GNN and transformers, are fighting with each other. So here's kind of like an attempt. Like, how do you feed a graph into a transformer? Okay, if you think about that, text is a chain graph. One work points to the other. So using the position, it makes sense. But when it comes to graphs, graphs are not linear. They're not chains. They obviously move in different directions. Like, how do I encode this into the transformer? So I won't get into the details, but it kind of like talks about how to put that into the first layers. Okay. This paper talks about this idea of, we've seen a lot of papers 2 years ago, or 1 year ago, 2021, yes, about linear time. It was kind of like the fashion. Can we have a transformer in linear time? So that battle is not over, but the question is, so there's another architecture that talks about transformers in linear time. So this battle is not over, but the question is it worth it? Like, we see other, other directions over there. So the linear time, we're more about so that we can increase the context. So instead of putting 512 going to 8K, and you see that there's a big speed ups over here, 25x, 4.9. The question is, do you really need to go to 8K tokens context? We're going to see the next session is, I think the next session is question answering. And, there's some other competing techniques. Of course, even, so if you're competing the traditional transformer with a 512, you're about two times faster. So it's not insignificant. It's still useful. Okay, and that's kind of like a provocative paper over here. It says, do we really need expensive pre-training? So again, this is something that since the birth of BERT in 2018, I believe, we took it for granted that pre-training, large-scale pre-training is the way to go. But here they suggest something else. They say, well, take your domain, do a query, retrieve relevant, relevant topics or relevant documents, and do the pre-training plus your task objective together. Okay, so if you have the web, you don't really need to pre-train the web if you're gonna do, let's say, sentiment analysis. If you already have a training set for sentiment analysis, pick the relevant documents from the web with some simple keyword search and do the training. You do your pre-training plus your sentiment analysis. It's an interesting concept. Can argue with it. So question answering. So again, about 20 papers and a workshop called Knowledge Retrieval and Language Models. And I actually watched the whole workshop. It was one of the workshops that I watched end to end. And I picked some papers. They talked about the frozen language models with memory augmentation. This is the pre-training that we talked about. The Lambda, which is the big one that does the dialogue. The auto-regressive models. Again, worth going through that workshop. It was I really enjoyed it. But let's go through the papers here. So this paper, it's easy. I mean, we talked about it. When it comes to question answering, you really need to incorporate time, and this is kind of like a streaming Q&A where it changes, answers are changing over time. It's more like a workshop, more like a benchmark to help promote the research over here. This was a very clever idea. This idea here says, you have this question: who plays Joker in Dark Knight? Who plays Cobb in Inception? Who plays MJ in Spider-Man and No Way Home? So basically, all of these queries, they go through the same graph traversal pattern. So, you just find similar queries. So it's a GNN search, and you're trying to enforce the patterns. You got a movie, you got an actor, and these are the hops that you're doing to find out the answer. So, it's another way of augmenting it. You can see really boosts the hop queries. The results are really amazing over here. This one, neural symbolic models for logical queries and knowledge graphs. As far as I could tell, it basically uses a GNN to complete the facts. It uses fuzzy logic operations. It's an interesting idea. It's an interplay between symbolic and neural. They don't mix them completely. They just use the symbolic query decomposition so that they can go to the GNN and see the facts that they need. This is another direction. I put it in the neuro-symbolic. It's basically, we know that neural networks are able to execute programs. So here's kind of like a list of a few basic algorithms, and they're basically testing. It's a benchmark for testing different neural network transformers and etc. on how they do these tasks. Okay, that paper has an interesting author. Jürgen Smidubaba was one of the inventors of LSTM. So that looks like LSTM version 2.0. So this idea over here is like, again, in LSTM, basically, according to your previous states, you're changing states. So you can think about the neural network changing weights. Over here, they take it to the extreme where they have this self-referential matrices that as you're giving something as an input, they change for the next input. So it's a meta learning setup over here. Still in the concept of experimentation and vision. I think it's an interesting direction. Let's see where this is going to lead us. Okay, we see that almost every conference. This is an old idea, symbolic regression. Okay, symbolic regression, you're given the data and you're trying to find the formula that generates the data. Very popular in natural sciences. So, for example, you're given data, you're trying to find that this is, if I give you this, what's the expression that generated that? And usually the way it works is that you have a set of functions and operations, and you are trying to form the expression that generated that. So, for example, if you're using the hyperbolic arc sinusoid, the algorithm might come up with that expression, which turns out that this is the exact, or in some cases it gets into the asymptotic, like over here. But anyway, the problem is that so far we didn't really have a symbolic regression for recurrent sequences, or basically for recursion. Okay, so right now you're learning the recursion that generates that. Okay, so you see here the predicted. So it's trying to find the recursive relationship between the points. I don't want to get into the details. We saw a paper about combinatorial optimization on the self-supervision. But there were two interesting papers, one with reinforcement learning and talking about surrogates. So the idea is that if you have a really complicated objective function, combinatorial optimization, you can create a surrogate neural network, and then you use reinforcement learning to search the space. Okay, now that paper is very interesting because I did find it very practical. This is a problem. So it's called it's called smart predict plus optimize. If you work at any business problem, you do have forecasting, and then a forecasting problem. Let's say it's a supermarket, you're trying to predict the sales of the tomatoes, and then you have a decision problem about how many tomatoes should I order, when should I order them. It's usually a supply chain network. That kind of paradigm, you find it almost on every business. And one is a machine learning problem, okay, predictive problem, and the other is like an integer or a linear optimization. So predict and decide here, you see it. So this paper kind of like shows how you can symbolically use symbolic calculus to reduce the problem into an MILP, and it has some mind-blowing results as you get 2 orders of magnitude better solution. Now, what is even more mind-blowing is that no deep learning was used. So I think it's admirable that in the era of deep learning, where we're being so fascinated, people go back to more traditional business problem, and they solve them with techniques that have been there for years. Highly recommend it. Okay. Accelerating transformer-based QA systems. Here, the idea is that again in the non-parametric language models, you transform something, you put it in a transformer, you get the embedding, and you're doing a nearest neighbor computation. Again, look back to ICLR 2022. We make a special case about how to scale these problems, and with the rise of the new vector databases, how things are becoming better. Now, this one is basically making an observation that if you do a nearest neighbor query now for your next prediction, and you have to do another one, these nearest neighbor queries are correlated, so you shouldn't really start from scratch. So it takes that advantage. So if you do the first nearest neighbor lookup, then the second can be faster. Very interesting idea. Okay, this was also again theorem improvers. In my opinion, is part of the of reasoning of the neuro-symbolic world. And the biggest problem is finding labeled data over here. So this idea is that if you have any unsuccessful proofs, use them as training data, like consider the target, wherever, how far you went as your target and where you studied, and use that as training data. We saw exactly or almost exactly the same thing at ICLR 2022. Go back to the presentation, I'll just put it here for completeness. Another paper that was talking about this idea. Another interesting thing that we saw, it's called dialogue in painting. So basically, you take Wikipedia and you use networks that they can convert it to questions and answers. So basically, this idea is that they realize that as we write a document, basically you can see a document as a series of answering questions. Okay, so it's an interesting concept that this is how we write. Every statement is trying to answer a question. So it's not hard to train a network to recover that question. So by doing that, you basically create a very valuable training test set for question answering, because getting annotation is very hard. Now there's a whole lab at Stanford called Oval that have done the same thing with synthetic data. Highly recommended to go through that. So they don't use Wikipedia, but they create an ontology, and from that ontology, they create questions and answers. We don't have time to go through that, but interesting work, highly recommended. And then another classic problem in neuro-symbolic reasoning is rule induction. Okay, so basically, I give you facts and you discover rules. And again, there was a great paper at ICLR 2022 called R5. I didn't see comparison between these two papers, probably because they came within 3 months of difference, but this is super, super useful for any, you got a company with an enterprise database, taking these facts and making rules. It's very, very useful. We're getting closer. Negatives in knowledge graph embedding. So these methods were quite popular until a few years ago. They're called KGE, like Trans-C, Complex, and some others that basically take a knowledge graph and do an embedding. There was always a problem with the negatives. That was the sensitive part, and that paper over here gives the theoretical background. It's a little bit late in the game because transformers and GNNs have taken over, so these methods are not super popular anymore. They've been replaced. Okay, more than 3, but we kind of like handpick these 3 papers on hardware and AI. And in fact, we might do another presentation for MLCs, which was last week in Santa Clara. There's a whole conference talking about that, if you're interested. But that's kind of like, to me, the long and expensive bet to scalable AI. So there's different directions. Okay? So there's one direction that they're trying to code the current neural networks in FPGAs and hardware and make them super fast and maybe super sparse so that they're fast, but at the cost that, if a new architecture comes, then you have to create a new chip and how you can reprogram them. The other one is, it might be a much cheaper or more, energy from an perspective to mimic the brain with spike trains, because they're just spikes, they consume less energy. So there's papers trying to look at that. And the other one, you might have heard like the 1-bit neural networks, where basically, the most expensive operation is the multiplication. So if we can use bitwise operators like OR, AND, shifts, and do deep learning with those, that's like a big, big, big win. Okay, because then it becomes super, super, super fast on hardware. Even in software, but hardware becomes real. So it's another bet towards scalable AI, and might happen. Okay, we talked about generalization. So from this paper over here, there's a list of 11 papers. I won't go through all of them. There's 2 papers that I liked. One was how do you assign importance to points for deep learning predictions? So basically, let's say you have a data set, I don't know, 1 million, 10 million, 100 million points. And the idea is that you take samples, you train a model, you measure the performance. It's kind of like a way of pricing or finding valuable data points. So basically, your regressors has the data points. Let's say you pick this 1,000 points for this, you got performance, 10. Then you pick another 1,000 points, you got a different performance. So now you're basically building a linear regression problem. Based on the points, what's the performance that I'm getting? Okay, the accuracy, let's say. So now you can run lasso and you can find which points are the important ones and use those. Interesting technique. Now, our paper also something that triggered my caught my attention over here. That's because there's some interest in program analysis. So you probably have heard that neural networks are programs, and that was the term. I think it was called software engineering software 2.0. There was an article a few years ago. It was basically saying that the neural network is the program, like it's the knowledge is stored into the weights. So basically, what this paper is doing is basically finding rules, like if this node spikes, then this node also spikes. So it finds correlation between nodes, and it creates a dependency graph. Okay, and then it studies that graph. So I think it's in my opinion, it might be a new way of studying neural networks. I really like this approach. It's early. We'll see. So it's called the neuron dependency graph. Okay, and at last, this is more like an MLOps, optimizing your MLOps. So there's plenty of places where you can buy. So we talked about, this is the new trend, doing machine learnings with APIs. So you got your GPT-3 here, you got your Facebook there, or your Azure, or you got OCR system from Google, another one from Microsoft. And so the question, and they have different pricing. And here you're optimizing basically your cloud costs. Like you're trying to find the one that gives you the best results at the best price. So you just don't buy blindly. This is also an interesting area of research in machine learning, pricing data. Okay, out of distribution on detection with deep nearest neighbors. So this idea is that it's really simple. Basically, if you just look at the distribution of k nearest neighbor distance, you probably know that these points are in distribution because they always have someone near them, and these points they are out of distribution because their neighbor is always too far away. And here we're just like the way that you train your model with or without contrastive learning, you can make the out of distribution easier. Again, this is a very typical technique of finding out of distribution points. It's not, I think the innovation here is using deep learning. Okay, getting closer to the end. Drug discovery and proteins, plenty of papers, 22 papers. I couldn't go through all of them, and also besides that, three workshops. So we had already noticed that at ICLR that COVID and AlphaFold have sparked like the research in that area. And here actually we see the first workshop on healthcare AI and COVID-19. At last, the generative models, there's more papers on that. We didn't spend that much time, but the style gun is a very, made kind of like a revolution. So the style gun, you can read the original paper. The problem was like robustness. If you wanted to generate out of distribution, it wasn't working well, and it's kind of like a new architecture over here that generates guns, it generates images for out of distribution. But StyleGAN is one of the most popular networks. People use it a lot. I think I'm going to skip this paper. It has to do more with psychology, and I think we're close to the last. I think sparsity. Sparsity in general makes backpropagation harder, and it makes it harder because what can happen if you over prune and the output of a layer becomes 0, it's called layer collapse, then you can't backpropagate. Okay, so you reach a point. So the question is, can you increase your connections without hurting sparsity? So skip connections are well known for not really adding, because you're not adding more parameters, you're adding an extra connection. Okay, so they're not adding extra parameters, but they add extra connections. So this is kind of like an idea of providing more skip connections during training, and then you can actually remove them in the end, and they can use with any type of masking. I don't want to get into the details, but the way you prune is called masking. Anyway, it doesn't matter, but that's kind of like the idea. So you avoid this problem of layer collapse. And again, the lottery ticket, again, for those of you who might not know, there was this idea that you train a neural network. Once you train it, you remove all connections of low weight, okay? And then you train your network from the beginning, from the same seed, okay? So you don't change your initial point. You keep training the sparse one. So you basically train the network twice. So you don't avoid the big cloud costs of GPU costs of training the network, because you still have to train a dense network in the beginning and then retrain it as sparse. Okay, but it saves you a lot of cost on inference, because now your inference is on sparse data. Now, the idea is, they call it the lottery ticket. Okay, so the idea is that you have a high chances of discovering this lottery ticket early, and the idea is that you start pruning early and retrying. It's more like a more like a heuristic over here. Other people have also tried that, but there's some little differences that apparently make this technique more efficient. I was wrong. Again, we talked about backpropagation under review. This idea that the brain doesn't work like that. It only goes forward. It doesn't really backpropagate. So we shouldn't be doing that. And it's worth spending more time over here. So they say that it's much better to use a wide neural network. So, one depth, two layers, basically, but make it pretty wide. And it turns out that the error is, the backpropagation are equivalent to simplified learning rules are equivalent to backpropagation wide neural networks. So basically, some simple statistical measurements end up being equivalent to the backpropagation over here. So some people believe that we shouldn't really go very deeply, but we should go wide. It's an interesting direction. Okay, the reason why I picked that problem is, it's actually a mistake. It's a word mover, not word mover distance. Let's fix that. So we're going to fix it on the spot. So what happened was that there was this paper that originally said that, word movers is much better than TF-IDF and bag of words. And I don't know how, but somebody took a look at the paper and discovered there was a big mistake in the pre-processing of TF-IDF. They didn't do the pre-processing properly. So now that they did pre-processing properly, it turns out that the word mover distance and the TF-IDF, they're basically around the same. So that claim was wrong. So I just wanted to bring that up because it's actually a very popular distance in many problems that we don't really have we don't need the big deep learning complexity. But you know, it's an interesting recall over here. You know, reinforcement learning, I only I think have one slide, but there was a workshop, that was the other workshop that I watched from beginning to the end. It's called AI for agent-based modeling. So agent-based modeling is not exactly reinforcement learning. It can have reinforcement learning. It's basically the game of life or the cellular automata. There's plenty of books and papers written in the past. It's coming up. It's also linked to probabilistic programming as well. Very, very interesting workshop. And there you can find a very nice competition about agent-based modeling and climate, which I signed up. I don't know if I'm going to have time to participate, but another workshop that I went through. Interesting to see. Now, there's one thing that you should think about is that language models are invading to the RL space. And basically, here it kind of shows you how what they realize is that you can find instructions. You know, if you say throw away paper, walk to home office, walk to a waste basket, find a waste basket, grab a waste basket, walk to desk, drop paper in the waste basket. So basically, it describes the whole, like you set a goal, and it finds all the steps to achieve that goal. And that's generated through, you know, brush teeth, walk to bedroom, open door, walk to sink, put pot on sink, and blah, blah, blah. So they actually realized that that information existed already in pre-trained model. So workshop, other, you know, this is kind of like other papers, workshops, data perf, benchmarking data for data-centric AI. Again, look at, we have another presentation of data-centric AI. There was a workshop at NeurIPS last year. This is kind of like a continuation. This is more like a theoretical paper, but it basically says that throwing randomness to a neural network on its own can improve the efficacy. Again, let's just go quickly about constraint-based graph network simulator. So, you know, more and more kind of like interest in what people call accurate digital twins. And we saw a similar problem before. Now this is how do you sell data to a machine learner? What you should keep from here is that pricing data is not easy. And I think that's the last slide. This is a summary of all the workshops that we actually went through as we were talking about different areas. And here I would like to thank you for attending. This presentation, the slides are available. And if you want to dive into any of these topics, if you want to have me present at your team at a seminar and go into the direction that you find more interesting and customize it, I'll be very happy to do so. So thank you.